Feeling stuck with multiclass problems? SVM makes it simple. In this video, we'll break down SVM for multiclass classification with step-by-step implementation, making it easy to follow and apply. Welcome to Day 8 of the 30 Days of Machine Learning series. If you're just joining, don't worry. You can click right here to access the full playlist and catch up on every step of the journey so far. And hey, make sure to hit that subscribe button so the next video in this series drives straight into your feed. Starting with our core tools, Pandas for data, NumPy for math, Matplotlib for plots, and Seaborn for sleek visualizations. Using sklearn's shuffle function to randomize the data from train and test, ensuring our model trains and tests on diverse, unbiased samples. Checking for missing values in both train and test datasets, a crucial step to ensure data quality before proceeding further. Creating a frequency table to see how often each activity appears in the training dataset, giving us a quick data overview. Counting activity occurrences and organizing them into a data frame with labels and values, making the data easier to analyze visually. Now let's visualize the distribution of activities in our dataset using a pie chart. We first define the activity labels and their corresponding values, then assign distinct colors to each category for better clarity. The plt.py function is used to generate the chart, with customizations like shadows, percentage display, and label distances to make it visually appealing. The plt legend function adds a legend, so we can easily identify each activity. By setting the axis to equal, we ensure the pie chart is circular. Finally, plt.tightLayout ensures everything fits nicely, and we display the chart with plt.show. Here, we're preparing our training and testing data. We drop the activity and subject columns from the feature set, creating xtrain and xtest. Then, we extract the target labels, activity, from both the train and test datasets into ytrain label and ytest label. Checking the shape of our training and testing datasets to confirm the number of rows and columns before feeding them into the model. Here we're setting up the label encoder to convert categorical labels into numerical values for easier model processing. Fitting the encoder to our training labels, then transforming them into numerical values, making them ready for model training. Now we're fitting the encoder to the test labels and transforming them into numerical values, ensuring consistency with the training set. Here, we're extracting the numeric columns from the training data and printing the total count, giving us insight into the features. We're extracting the column names from our training data and storing them as a list, giving us the names of the predictors. We're applying standard scaler to standardize our data, making sure each feature has a mean of 0 and standard deviation of 1. The training data is scaled with fit.transform, while the test data is scaled using transform. We're setting up a parameter grid for grid search. It includes different kernel types, gamma values, and C values to fine-tune the SVM model. We're performing a grid search to find the best hyperparameters for our SVM model. Using cross-validation with 5 folds, we test different configurations of the kernel, gamma, and C values to optimize the model. Finally, we fit the model to the scaled training data for the best performance. Here, we're checking the results from the grid search. The best score achieved, the optimal C value, kernel type, and gamma. This helps us understand which parameters gave the best performance for our SVM model. We're using the best model from grid search for final predictions on the scaled test data. The predictions are then converted back to their original labels using the inverse transformation of the encoder for easier interpretation. We're evaluating the model's performance by printing the confusion matrix, which shows the true positives, false positives, and more. The classification report provides detailed metrics like precision, recall, and F1 score, helping us understand how well the model is doing. Next, we check the training and testing set scores for the final model, giving us an idea of how well it generalizes to unseen data. The training score tells us how the model performed on the data it was trained on, while the testing score shows how it performed on the unseen test data. Finally, we display the model's score. And that's a wrap on our SVM journey. We've gone from data prep to model evaluation, optimizing our SVM for multi-class classification. But wait, don't go just yet. In the next video, we'll dive into decision trees, a powerful and interpretable model. You'll see how it splits data, making decisions just like you would. Click on the screen to continue and unlock more machine learning secrets.